Alright, let's look at the rest of our probability notes on page 5 and do some conditional probability. The probability of an event, we'll call it E2, occurring, given that another event, E1, has already occurred, can be given by the formula, and I'm going to read this the way it would read out. The probability of event 2 given E1's already occurred, so that's what that notation means, equals the probability of E2 and E1. So the probability that both events would occur, divided by the probability that just event 1 has occurred. There's two different ways to look at this, and if you watch the videos, he goes through these really well. So I don't think his videos are too bad on these, but I'll try to reiterate it a little bit here. So for method 1, it just uses simple probability, which is where we take the favorable outcomes and we divide by the total possible number of outcomes. So without having to use the fancy formula, we can just basically use our basic understanding of probability. You roll one 6-sided die. What is the probability of a 3, given that you know the number is odd? So I throw a die and I say, oh, it's an odd number. You automatically know that it's one of 3 possibilities. So what's the probability that the number I'm looking at on that die is a 3? So how many 3s are there on a die? Well, there's only one. And then instead of doing all 6 possibilities on our die, we're just going to talk about the 3 odd numbers. So the probability for this situation is 1/3, because we have 1 3 out of 3 odd numbers. The other way you could do this problem is by using the formula. So the probability of getting a 3 given the fact that it's odd. So first of all, we need the probability that it's both a 3 and odd. So what's the probability of that happening? Well, obviously 3 is an odd number, and there's 1 3. So that is a probability of 1/6, because there's 6 numbers on our die. So then the probability of the first event would be the probability that it's an odd number. So there are 3 odd numbers out of 6. That means there are 3 out of 6 possibilities. We're dividing 2 different probabilities here, which means we're dividing fractions. When we divide fractions, we can write down the top fraction, multiply, and flip over the bottom fraction and multiply the reciprocal. That would give us 6/18, which reduces to 1/3. Or you could even think about the fact that those 6's are going to reduce out. 6 divided by 6 is 1. So in the overall scheme of these multiplied fractions, we can take out those 6's right now, and we're left with 1/3. So we got the same exact answer by using the formula as we did by just thinking through the problem. So why wouldn't we always do a problem this way? Well, it depends on what kind of information we have. Look in this next example, they give us exactly the right information for us to do it using the second method. At P-Town High School, the probability that a student takes a computer programming and Spanish class is 0.15. The probability that a student takes computer programming is 0.4. What is the probability that a student takes Spanish, given that the student is taking computer programming? So the probability of Spanish, given they're taking computer programming, is going to be the probability of Spanish and computer programming divided by the probability of computer programming. That's just using this formula, right? So the probability of a student taking Spanish and computer programming is 0.15. The probability of a student taking computer programming is 0.4. So the probability that one of those computer programming students is in Spanish would be found by taking these two numbers and dividing them. So taking my calculator, I get 0.15 divided by 0.4, which divides out to 0.375, or a 37.5% chance. So a little over a third of any given computer programming student would also be in Spanish at this school. We're going to keep going over on to page 6. Here are the results of a survey completed with adult parents with children. So we have parents of children that are in college, and we have parents of children that are not in college. Now, of those parents, we have various opinions. We have parents that think college is too expensive. We have parents who think college is affordable. And we have parents who think that college doesn't cost as much as it should. So, we're going to try to find the probability that a person thinks college is too expensive, given that they have a kid in college. Alright, so the first thing we're going to do is look at the probability. Let's go ahead and set this up with our formula. So we're going to try and find the probability that it's too expensive given that they have a child in college. So to use our formula, the first thing we need is the probability of both having a child in college and believing that's too expensive. So for it to be a child in college, it has to be this first row. So there's 55% that have a child in college and believe it to be too expensive. So this is both of those things right there. This is this and this is that 55%. So the probability of both things is 55%, so 0.55. Then we're going to divide by the probability of just having a child in college. So again, that would be this second row. However, instead of it just being those who believe it's too expensive, it would also include this 4% who find it affordable. So 55% plus 4% would be a total of 59% of parents surveyed that have a child in college. So we would divide that by 0.59. So the top probability is the probability of having both a child in college and finding it too expensive. Then we're dividing by the probability of just having a child in college. And that will give us the probability of a parent thinking it's too expensive given that they have a child in college. So then we divide those two numbers and we get 0.932, which is a pretty high 93.2% of parents surveyed in this little survey that believe college is too expensive given the fact that they have a child in college. Okay, 2 cards are drawn without replacement in succession. What is the probability that the second card drawn is an ace, given that the first card drawn was an ace? So we can do this using the formula, or we can just use our simple probability formula. So if the first card drawn is an ace, that means that our deck of cards goes from 52 cards to only 51 cards, and our number of aces goes from 4 aces to 3 aces. So what's the probability of drawing an ace after an ace has already been drawn? Well, it's going to be 3 out of 51 because that one ace is already gone. We now have 51 cards and 3 aces left. So we have a 3 out of 51 possibility of drawing a card that's an ace, given the fact that one of the aces is already out of the deck. Next, 2 cards are drawn without replacement. What is the probability the second card is a red face card, given the first card is a red face card? Now, if you watch the author of the book on his video of this, he makes a mistake. So in order for me to correct the mistake that he makes in his video, we're actually going to take out the word red, because he does the problem just given that it's a face card, not that it's a particular color of face card. So, you know how we have 12 face cards in the deck? So 12 out of 52 cards in the deck are face cards, right? However, if we take one of those cards out to begin with, we now have one of our 12 face cards gone and one of our 52 cards gone. So we now have 11 out of 51 face cards left in the deck instead of 12 out of 52. So 2 cards are drawn without replacement. What's the probability the second card is a face card, given the first card is a face card? So the first card is gone, it was a face card, we're down to this probability right here. So see how you don't always have to use the weird formula? Sometimes you can just think through in terms of what's left in your sample space and how many possibilities there are left.